All right. Eric was really good in the other classroom. Can we go back a little bit? I want to set the stage a little bit more. More. I want to go back to the figure. More. Okay, right here. What I talked about yesterday was predicting the incident solar radiation. And we talked about the Excel sheet. I talked about energy systems and what it takes to integrate them with economics. We need to worry about technical. We need to worry about policy and getting people to accept them. And I also talked about the need for an accurate model. And the previous speaker, Eduardo, that was near and dear to my heart. Yesterday when I said thermal radiation and heat transfer, the radiative transport equation and radiation in participating media was exactly what I was talking about. So it was very, very interesting, or good talk. But you need accurate models. We need accurate simulation. And one of the things that occurred in the literature was in this chamber where we have moist air, we're adding more and more moisture to the air, water, and we want to condense it. Modeling this particular chamber requires both mass balances, psychometrics, and the question is, do we have to go through all of that? Can we simplify things? Can we go back now? So we went through the models, the radiation, the temperatures, and this was a comparison that I was rushing yesterday. This is comparing the model with the in-detailed chamber model, where it says no chamber. That's the 2 degrees C assumed temperature difference model. And what you can see is, if I look at the July data, I'm getting a significant difference in the daily freshwater production between modeling it with all the physics and making a simplifying assumption. And it's this type of assumption that can get us into a lot of trouble when we start doing simulations, because we're trying to develop a product that is going to be different or competing with the reverse osmosis. If I made the no chamber model, my model predicts 22% higher output. And guess what? That might say, hey, this was better than reverse osmosis, when in fact it isn't. So you need to be aware of the accuracy of the models. I feel so disrespectful. I keep referring to the previous speaker by his first name, Ramos. Professor Ramos. He deserves the respect. When he was looking at his simplified models and looking at trends, and he gave a very good explanation of the value. It gives you some basis to move forward. When we come to energy systems and comparing alternatives, you have to be aware of those assumptions and what role they play. Are they negligible? in this case, we need to include the model. May we go on? So I forgot this was here. So we're looking at this simplified tray model. And let's go to the next slide. What we did was include the chamber model, bring in the Boston solar radiation data, and we looked at comparing the pool evaporator, that very simple design, with the tray design. Is the tray design better? That's the question. And if you look at these results, the tray design are in the blue. The pool evaporator, that very simple design, is in the red. And you can see that there's a significant difference, especially in the summer months, between the two designs. In fact, we're almost a factor of 2 better with the tray design in the summer. So this was very encouraging. Now, we also have to realize, comparing the two designs, I now have a very complicated manufacturing process to make those trays, attach them to the absorber plate. But I see a significant improvement. But how good is good? Can I have the next slide? Okay. And how does this compare to the reverse osmosis? And you asked me at the end of the presentation yesterday, was it you or you? What are we comparing this mini project to? Well, I'm going to answer that question now. On this table, I'm comparing the reverse osmosis output to the tray in July and December. And if I look at the reverse osmosis, I gave you this number, it produces 66 cubic meters per hour. But we want to know how much it's going to produce per day. And again, the reverse osmosis, single design point. We just multiply by 24 hours, run it constantly, and these systems are designed to run continuously, except for scheduled maintenance. It is going to produce 1,584 cubic meters per day. Now, the solar collector trays that I'm describing are only 1 square meter. The idea is I build modules, individuals, and then put them all in parallel. Put them on my floating barge. So the trays, putting in terms of the same volumetric flow, are only putting out 2, 3, 1,000ths of a meter cube per day. This is going to take a few solar collectors. In December, it gets even worse. And the reason for the asterisk is this is meter cube per day per square meter of collector. Now, the power, I have to supply. I have to come up, or rather, you have to come up with providing 85 kilowatts per every hour, or the daily energy consumption, 24 hours times that, of 2,040 kilowatt hours. And the modification to the mini project, the addition, What I want you to think of is you install your solar collector fields, you collect energy and have a perfect storage medium, and we'll use that energy to supply this power for the next day. Again, this what I just said is why renewables, variable sources, could really complicate our lives. Because in this case, it isn't a matter of plugging into the plug. I have to collect energy that varies over the time. Now, in the solar, I have no other power input. The area, I'm assuming, for pumps, stored water, is basically going to be the same. And I didn't put that down. For the reverse osmosis, let's assume fossil fuel. And I don't have a capital investment. Okay, I don't have the economics for this. But let me just finish the chart. The area that I would require in July for my solar trays, I just remember the ballpark number. I want to give it exact. Is 5.4 times 10 to the fifth square meters. Anyone have an idea how big that is? No? I don't either, but I'm getting kind of lost in 10 to the fifth. This represents approximately 50 soccer fields. Okay? If you look at December, and if you're designing this, people drink water in December as well as July, right? It'd be 2.6 times 10 to the sixth. That's 244 soccer fields. Okay? I can't recall seeing any playing fields that would correspond to 244 soccer fields. Yes, I don't burn any fossil fuel. And my operating energy source is free. I have to pay a lot of money to buy this land. More importantly, and I was talking to Sergio on one of our drives, and he mentioned how in 7 years, the area around Salamanca, you have a lot more industry that has come in. It has displaced what? Farmland. There's still a lot of farmland around Salamanca, and I seem to recall some wonderful produce and fresh food that I have had here. Are you willing to give up that farmland to put in solar collectors? Now, granted, the farmland might also need fresh water, but you start to see how it isn't just the cost, it's what you're giving up. By the way, if I assume, and it's a very low estimate, that for every square meter of my collector plus land would be $2,500 per square meter, US dollars. Okay, multiply that by approximately 20 to get pesos. $2,500 per square meters. This project would cost around $160 billion. Pardon? No, this is for the collectors and land. Okay? Installed. That's quite an investment. And even if it lasted 20 years, how large is Salamanca? How many people live here? No. Yeah, I know several of you. What's the population? Is it 150,000 residents who now would have this amount of fresh water, probably not enough. But start to divide 150 billion by 20 by 150,000, and your water costs are fairly significant. Not sure what the reverse osmosis plant will cost. But this is one of the things that you need to think about with renewables, and I fully support renewables. I don't want to give you the idea that I'm trying to discourage renewables, but as engineers that want to solve problems, we have to come up with solutions that people will implement. And to just divert here, I wasn't born, I read this in a book, so okay. In the 1920s and 1930s, every home in Florida, in the United States, in the southern part of the United States, had a solar hot water heating system. And the customer psychology, remember that ellipse. People would not buy a house unless it came with a solar hot water heater. And they were incorporated in the attics, and the panels were on the roofs. And today, you can barely find a solar hot water heater. What happened? Yes, we have solar pool heaters, okay, of various designs. But what happened? Why did people stop using this technology? And it was crude. It probably could have been improved. But why did they stop? Well, what happened in the 1929, 1930? Because it also happened in Mexico. The Great Depression. And in the United States, one of the actions that were taken, the government instituted large public works project. And around this time, go back to Professor Lienhard's early lecture, you never know what invention comes up. Well, Edison, Tesla, fought over AC, DC current, electrification. We have all these rivers that are flooding. We need to put people to work. Let's build large dams and produce hydropower in southeastern United States. And this was called the Tennessee Valley Authority. So great. We have all this electricity. nothing to use it with. So the electric utility companies actually became appliance dealers. They would sell electric hot water heaters, irons, electric stoves, the cooking utensil of the future. I don't think they quite got to refrigerators. But what happened is, in order to sell electricity, they literally gave away electric hot water heaters. So they electrified your house, gave you a hot water heater, and suddenly you had a rusting tank in your attic that just became an eyesore. And it totally, the use of solar for hot water heating totally went out of acceptance. Now it was a hot water heater. Today it's a natural gas fired hot water heater. Things change. That customer psychology, people's perceptions. So it's not just about money. You have that societal impact. And when I look at these results and I'm trying to spin them in some way that I don't feel embarrassed up here, a multi-billion-dollar project that's going to take up 240 soccer fields, is this the best that we can do? May I have the next slide? Oh, I'm sorry. Leave it there. Is this the best that we can do? Because if it isn't, how good can we make this? And can it become competitive? Now, one of the other results, just to show you that you can mine these simulations, this was comparing the water in the pool and the glass. These are the two major temperatures. One affects condensation, one affects the evaporation rate. And you can see how, with the tray design, there's a built-in storage effect that we weren't anticipating. Yes, we produce lower temperatures in the water, but we produce more fresh water. And if you notice, the red lines continue producing fresh water a little bit longer than the blue lines. And the reason for that is we have a more massive absorber plate that displaces the peak temperature slightly. And this indicates that, well, maybe we should be looking at some of the mass of these units. Maybe we can take advantage of this. And again, the idea is, can we do better? And this is where the second law comes in. And this is all, okay? It sets our operating limits. And you've heard some of this before. It identifies where the losses and irreversibilities are happening. A roadmap to making us better. Is the source matched to the load? And I mentioned yesterday, all of these are tied to sustainability. And the two terms, the parameters that we want to look at are exergy destruction or entropy production. We also want to look at a second law efficiency. And that's what both Professor Lienhard was quoting and what I have been quoting in my presentations, our second law efficiencies. The second law is, how many of you have had thermodynamics in the second law? Okay. I am going to pick on one of you. Are you very comfortable with the second law? You are as comfortable are you as with the first law? If I asked you to calculate the exergy destruction that I'm producing as I lecture to you, would you be able to do that? Okay. You're better than my students. Okay? Usually, we don't have the intuitive feel of the second law. And we're told all these one-line statements. Okay? The most popular one is second law. You always lose, and you never break even. Right? And the little sidebar, you have to play the game. Okay? You can't opt out. Well, that's true. There's nothing wrong in that statement. And then we get a little more formal. You cannot operate a power-producing device with a single heat reservoir. You need a heat rejection. And I'll come back to that. But the second law has a lot of subtleties that don't exist in the first law. And we almost always revert to the first law for design. So I thought I'd just take a little sidetrack and seeing how many people have not had thermodynamics. And I met an individual this summer who had a really good way of introducing the second law and this wonderful property, entropy. May I have the next slide? We're all familiar with gas gauges. We all can think of energy being conserved and being in our gas tank. We think of oil reserves in a country and how do they match the energy consumption. I want you to think about this second law property, entropy, and an entropy gauge. If we could have a measure like a fuel tank gauge, we might have some energy here, and we have a higher energy source that we use to increase the usefulness of that energy. We can't increase the energy, but we can bring in two energy sources and produce one type of energy, say electric power, heat, second form. But when we do that, we always have some unrecovered energy. We only move in one direction. Things are not reversible. And as a result, this entropy gauge, and entropy very often is said to be, it's a measure of the disorder in the system, would increase. But now we have higher energy sources. We have this electrical power, and we're going to divert it and do some other energy transformation, and we have energy rejected or recovered, but we also have unrecovered. Again, it's not reversible. And this entropy meter would go up. And everything is centering about this entropy property. And I again went back to a general explanation that it's a measure of disorder. But let's keep it really formal. Can I go to the next slide? And by the way, I forgot on that slide. Dr. Andrew Foley is a professor at the U.S. Coast Guard Academy, and he probably does this much better than I. But what I want you to think about is a flow, a fluid flow, that goes through a system and encounters a restriction that we call an orifice plate. And this restriction alters the flow, causes a pressure drop, and the flow, the energy in the flow, takes on a different form as it moves through. Now, when I talk about energy, I'm talking about internal energy, flow energy, potential energy, and kinetic energy. I want you to imagine that this tube is a straw, and you have a really good beverage that you're drinking through the straw, and somebody comes along and pinches it down. So when you're drinking through it, you're getting all the fluid, and all of a sudden, you get the pinch down, and the flow changes, the velocity changes. It's harder to pull the flow through. Now, the first law says that the change in this energy, there's no work, no power, no heat. The change in this energy is going to be equal, or must be equal, to zero. That's what the first law says. And when you break it down into each of these forms, you have a change in internal energy. You have a change in the flow work, pressure times specific volume. You have a change in the flow work, another form, that is VdP. You have a change in potential energy and kinetic energy. And when you think about these energy changes, potential energy is reversible. Okay? You're getting sensitive. I was going to say if I drop my phone, but if I have something at a high potential energy, lower it, I can extract energy from it. If I move it back, it takes the same energy to bring it back up. The same with kinetic energy. These are reversible. Okay? I can store them. I can have a rotating flywheel that stores kinetic energy. I can pump water up a mountain into a reservoir to save potential energy. This term VdP, think of it as a pressure spring. Okay? You have an incompressible material, specific volume isn't going to compress. When you decrease a volume, you increase the pressure. If you release it, you're going to recover that energy. It's the pressure times the change in specific volume or density. And this change in internal energy that isn't fully recoverable. And if I consider those two terms and I divide them by the temperature, I come up with the property that we call entropy. It's du divided by T, P dV divided by V. So, T. This grouping, when you look at this simple problem and break it down into what's reversible and what is not recoverable, and divide it by the temperature, we come up with entropy. And we all accept energy terms. What I want you to do is just accept entropy. It's a thermodynamic property. And we can use it to describe things. May I have the next slide? Also, by Dr. Foley. If I start taking in entropy accounting, when I have the first law, I have my system of interest. This room, all of us. The energy in this room is changing as a function of time. I hope I'm not increasing the decrease in energy, okay? But it does that by interchanging with the surroundings. And when you do an energy balance, the rate of change of energy in the system must exactly equal the rate of change of the energy in the surroundings. Energy is conserved. We know that. But let's go to entropy. If I look at the entropy change in my system with respect to time, and keep in mind that some of this entropy stops being recoverable. My system has to interact with the surroundings. That is an important statement. The system must interact with the surroundings. That means there's a rate of change of entropy in the surroundings. The problem is, or the challenge, usefulness, is that these changes no longer are equal. In fact, when I add together these two changes, they don't sum to zero. They're not conserved. It actually increases. So in a real system, the rate of entropy must be increasing. But there's another part of the story. Notice this statement involves the system and the surroundings. And this screen projection is fantastic for this. This is what many people do. Here's my system. Let's do an entropy accounting on it. And you notice what I'm blocking here. And I hope it's being picked up on the video. I'm hiding the surroundings. And we focus on all the interactions that come from the system. Heat, the entropy that heat carries, all of that. And we forget about the surroundings. When it comes to energy systems, and when you hear about perpetual motion machines, people forget about the surroundings. They don't include them. I'd like to think of it as being not defining a complete system. Because you can very easily come up, define a system, and get an entropy to increase in the system during a process that doesn't violate the second law, because there's going to be a larger corresponding decrease or increase in the surroundings. The second law, if you start thinking in terms of it, automatically will force you into taking a very complete system view. And this is important. Can I have the next slide? Everyone take a really deep breath. If you have any caffeine products, please take them. Here's my gauge. Entropy is, it's an important key measure. But what we also have to do, or what is a valuable tool, is something we call exergy. And it's related to entropy. Exergy is the maximum possible rate of useful energy that we can get from any state or any material at a given state. So, if I bring in a very large tank of hot water, it has a certain amount of useful energy that I could extract from it. Is it sunny out and warm? Or are you harassing me yet? No. No, I know on time. Sun. Is there sun outside? No. Okay. I'm being blamed for this. Sorry. Okay. How much useful work could I get from that hot water? Or that heat source? Or the sun? That's what exergy provides. And let's again look at E as representing the enthalpy, includes the flow work, potential, and kinetic energy. And if I take any device, what I'm going to do is look at the entering energy, my hot water. And in this device, I'm going to convert it to work out. I'm going to have a flow of energy out and a heat flow out. But what I'm also going to do is to define a dead state. And we could go off on a big philosophical tangent. Usually the dead state is the local surroundings. I can't cool this hot water to a temperature lower than the outside temperature. Okay? That limits how much I can cool or use this high energy coming in. So I can do an energy balance. And I told you this was a packed slide because I wanted it all on one slide. And the energy balance is going to relate the difference between the energy flows in and out, to work, to heat. If I do an entropy balance on this device, I will have the flow of entropy that comes in. I will have an entropy production term. What is this entropy production? Okay? It's our correction factor. It's our cheat factor. I want the entropy balance, and the reason I put it in quotes, entropy, the second law, is an inequality. Okay? If I come and I tell you that in the class that you're going to go to this afternoon, you're going to have an exam, don't look like, what do you know that I don't? I'm making it up. And what if I tell you that the grade on your exam will be less than 100? Have I given you any useful information? No. Less than 100. Everybody gets less than 100. If I tell you, I don't know you, okay, so I have no idea. If I tell you that your grade will equal 85, have I given you useful information? Yes. Your grade is 25. Okay? The average was 20, by the way. Okay? So, when I state equalities, I have something useful. Inequalities, it doesn't work. So what we do is to introduce entropy production. It's what makes this an equality. Entropy flows with the heat flow divided by T. Yeah, that's a term. Who's the gentleman that said he felt comfortable with the second law? Okay. I don't think we necessarily gave you this integral without saying that it was at a constant temperature. But in most processes, this temperature varies. Okay, so that introduces another complexity. And then we have the entropy flow out. How, in a perfect world, entropy production would be zero. I would produce no additional entropy. That's the ideal limit. I hit one of my major bullets. We have a limit. We still have this integral. And this is something, I don't know, I've started doing it with my students. We get locked into writing system sketches, control volumes for our problems, for the first law. But the second law then introduces this integral, which is a real complication, when in fact this Q out usually does nothing. It just has to be there to make the process work. But we get no useful energy out of it. So what I normally do is, if I'm not going to use this heat flow, I extend my system boundary, that's what this dashed line is, to where it includes the atmosphere, and I observe this heat flow at T0, the dead state temperature. And what that does is to make this temperature constant. I then have the integral of del Q, which is just Q, and I can now solve for that Q as equaling the temperature times the entropy production and the temperature times the entropy difference. That means I can eliminate this Q in my energy balance. And I've also put a marker in this equation. Entropy production. What is the best that I can do with this device? How can I make sure I have the maximum possible work power coming out of this device? What would be the value of entropy production? 0. So my maximum work output, which by definition is exergy, is now related to the change in the energy in and out minus T0 times the change in entropy. And we have a way of now writing exergy balances. Can I go to the next slide? We also have some tools for looking at different exergy flows. This large box here is my solar collector. I have exergy that flows in with the water. Oh, wait a minute. The wait a minute was planned, okay? This wasn't just, oh my God, what am I going to say? I want your attention. When I did the first law analysis, I just said, let's treat seawater as a single material. It had a certain value of the latent heat. And it produces an accurate model. But when I come to the second law, an exergy analysis, I have to take into account the exergy, how much useful energy I have to expend to separate salt from water. That means I can't avoid treating at the exergy level. Second law, I need to treat seawater as a mixture of water and salt. And depending on the type of salt, as you saw in yesterday's lecture by Professor Lienhardt, this is going to bring in all types of chemical potentials and Gibbs functions that I need to include in these calculations. But basically, I have my exergy flow in the salt and the water. I have exergy that flows out with the heat loss from the collector. And this is going to be related to the Q loss and the exergy flow associated with that heat loss. And again, I'm looking at it at T naught. The same for the condensation heat flow. And that's what these little boxes are. And then coming off of my system, I have hot brine. And you saw, just to refresh your memory from yesterday, we went through it very quickly today. This brine is coming out at about 70 degrees C at noontime. And it then will come to equilibrium, steady state, with the surroundings, T naught. And I put this box in here to extend my system boundary to the dead state, similar for fresh water. And what I have now, this dashed line, is my system for my exergy analysis. And I will quick, and it's complete. Notice it's all entering from the dead state, leaving at the dead state. I've included that ellipse that I blocked up here that was the surroundings. I have a complete system. Having that is what prevents you from being embarrassed with devising a system that has a hidden energy source. Dr. Foley had a really interesting story. He used to work for Rolls-Royce. And Rolls-Royce had a policy where every crazy invention that somebody sent in to the public relations department had to be reviewed by the engineering staff. The engineering staff loved it because some of the ideas actually got incorporated and some were just perpetual motion machines. The one that stuck in his mind was the rabbit farmer who, to keep the rabbits warm or ventilated, installed a photovoltaic system that operated a ventilating fan. Sounds pretty clever. He then discovered that he was producing more energy than he was getting from the sun. So he wrote this in that he had discovered a way to collect and increase solar energy. And he sent in a video of his rabbit hutch, complete with all the rabbit droppings, everything. And to take the picture, he put a great big electric spotlight to illuminate it. Well, guess why he got more energy out of the system than the sun put in? Anyone? The light. He was adding heat. He didn't have a complete system. He didn't account for that additional energy flow. These are the things that, when you get complicated systems, creep up. You want to? The cold fusion experiment. I was going to be kind to our colleagues in Utah. Yep. Now I have to go. I get 2 minutes extra. Okay? Okay, back in the 1980s, right after some of the oil embargoes, there was a group that claimed to have observed and successfully created cold fusion. Okay, the magic word in nuclear energy. Fusion. but they were doing it at room temperature in their laboratory, and they had videos, again, of their beakers and mixing the materials and showing that they had produced a net energy output. And it created quite a stir. It hit all the major newspapers, journals, and as soon as it happened, there were many, many detractors that said, this is impossible. They did something wrong. And as good science, people tried to duplicate it, and everyone failed. Yeah. ASME actually devoted a session. You didn't know that? Okay, then I'll go into this. They devoted a session right at the peak of all the controversy, and the investigators claimed that they would bring in incontrovertible proof, and it was billed as either it works or it doesn't work. Very well attended, created a lot of excitement, and the authors pulled out at the last minute. However, because customer psychology, 5 years ASME ran a cold fusion session. And no, and it actually was measurement error that led to it. So again, duplicate your experiment, okay? Now, just hit enter. The red line is incorrect, but it's a point I want to drive home. Many people would draw the exergy system with this red line, and they would then take the exergy that flowed out with the brine and the fresh water and just say, well, I'm including it correctly in the system. The problem is, if you don't use this exergy for anything, it should be an exergy destroyed term. And I'll say more about that on the next slide. How you set up your system becomes important. So if I look at my overall system, and this includes a transient term, in order to balance the exergy flow, the exergy equation, I introduce a term, exergy destruction. It's related to entropy production, but it equals the difference in the exergy in minus the exergy out. And I write this for the entire system. I then need to look at the exergy flow with the heat loss, which is simply related to the Carnot cycles. But something I said before, how much time do I have? Half an hour? Okay. I can be slow. I said 2. Okay. I'll do 2. 10. Okay. Going down rapidly. Okay, in this exergy balance, we have the exergy flow of the brine and the exergy flow in. These are mixtures. So I need to look at how much of the exergy flowing out is salt. This is the mole fraction of salt, times the exergy of that salt related to the dead state, a reference state, plus the fraction flowing out of the brine, that is water. And if you notice, I now am getting into, I have a couple chemical engineers in here. Okay. you're comfortable when I say mole fractions, moles. The rest of you mechanical engineers, chemistry. Okay? My message to you is we don't live in a world, and energy systems and energy storage systems are quickly going to become mixtures, compounds. You heard Professor Ramos talk about zinc oxide. He left out the word catalyst, but I think that's because we're mechanical engineers. These are waves of the future. So pay attention in chemistry is my message. Don't be afraid of it. Yes, we all went into mechanical engineering and not chemical engineering for a reason. But we need to embrace it. And finally, the exergy of the fresh water is just a pure material. What I want to emphasize, exergy destruction. This is what balances our exergy, our second law statement. It gets rid of that inequality. It's what measures what we're doing well or bad. So, next slide. The exergy. Solar energy has exergy. Many people consider it as a straight radiation heat flow that would be described by a Carnot efficiency between 5,800 degrees K and and the dead state temperature. This individual, Petala, has expressed the exergy in the solar radiation in this format. What he did is he looked at it as a cloud of photons and treated it as a gas. He's claiming we should not treat it as a heat flow. The difference between the two treatments is less than 5%. But we decided we'd go with this little more accurate statement. And finally, the second law efficiency, epsilon 2, is 1 minus all of the exergy destroyed in my complete system, divided by the exergy that flows in. Okay. So what does this tell us? Well, I looked at the pool and the tray design. The tray design produces much more water than the pool design. The second law, efficiency. Can you go back 2 slides? One more. Okay? The red line is the product system. This is incorrect because we're neglecting exergy that's flowing out of the system and what happens in the surrounding. The complete system is the gray. Okay, please go back to the table. The second law efficiency on the product approach is 6.65%. This is better than the reverse osmosis. It's incorrect, but it's better. The pool design performs much lower, but it's still in the reverse osmosis range. Well, we wanted to be correct. When we looked at the actual second law efficiency for the complete system, the second law efficiency drops down to 0.63%, under 1%. That's not very good. Similar drop for the pool. The tray definitely is better performing than the pool, but we already know that. And one of the reasons is because it has a larger evaporator area per incident area. But this difference between the product and the complete system is telling us one important thing. I have a few minutes, so I can play the audience. What is this telling us? Remember, the second law of efficiency is I add up all the exergy destroyed in my tray collector, the exergy that is leaving, that I don't use, and the exergy destroyed in the heat transfer. Why this big difference between that product approach and the second law of efficiency and the complete approach? Can you go back to the system sketch? Yeah. Yes. That's exactly correct. When I look at each of these exergy destruction terms, this exergy destroyed in the brine flow, this hot flow out, is one of the largest exergy destruction terms in the system. And that, can we move on? And that's why we see that difference. This is telling me how I should improve it. And can you go to the next slide? Oops, we had to skip one. Go back one. Move forward. I'm missing a slide. Go down. Go down. Ah. These two are out of order. I apologize. What we did was to put a heat exchanger, very simple heat exchanger, that only operated off the brine because that was the major flow. We took the hot brine, put it through the heat exchanger, and then discharged it. Brought, okay, going out here, we preheated the incoming seawater, and we've only looked at the complete system. What the earlier analysis did was to say, I was throwing away a lot of exergy here. So move up one slide. If I take the recovery system, and I again look, I'm sorry, this is December. Move forward. Move forward. Okay. When I look at what happens with the energy recovery, and I'm only looking at the tray, that's my better system. What I see in blue is the system without the heat exchanger, non-recovery. The recovery system has the heat exchanger. We get almost twice as much water production in both December and July. That's the main purpose of this. Go one more slide. The salt, this just shows the salt concentration, the salt temperature rise between no exchanger, we're up around 66 degrees max. With the heat exchanger, it happens earlier, and it's close to 30 degrees. By the way, the external temperature here is 19. Move one. The salt concentration. You notice that as I remove water, I'm increasing my salt concentration. I'll come back to that at the end. Please. No, forward. One more. Tray design. I'm producing 6 kilograms per day instead of 2.8. My second law efficiency went from 0.63 to 2.9, 2.79. Not quite reverse osmosis, but keep in mind, I'm including the primary energy source. The other figure didn't. To make my simulation work, Yesterday I said that we operated the collector to exit with temperatures below 100 degrees C, no boiling, and that actually had water leaving. To run the system with the recovery, we had to increase the mass flow by almost over a factor of 2. What the second law allowed me to do, and what I want you to be taking away from this, is it guided me into a means to improve the performance. Yes, I've increased my cost. Okay? Can we have one more slide? But I've decreased my area. Okay? Now in July, I think I need 25 soccer fields. But I also reduced the cost factor. And I still am apparently not at the same second law efficiency as the reverse osmosis. But this is not a valid comparison, apples and oranges. My tray, my analysis, solar still, includes the primary energy source. I haven't included that is not included in the reverse osmosis. And if you think that most power plants only work at 30% efficiency, you can see that this number is going to go down. I might add that in the next, did we set a date for when you're going to hand in the mini project? Nobody's going to ask me that question. You're going to just, 6 months from now. Oh, if you could have that done by next Tuesday and submit it, that would be great. What you're going to be doing is adding a power source. Happens to be photovoltaic. And I will now have a number for the next presentation of both this reverse osmosis plant as well as the primary source. Can I go to the slides? I want to get through this and then open up for questions. I've rambled for 2 days. What do I want you to leave with? I don't want you to leave with being an expert on solar desalination or calculating incident solar radiation. But what I want you to do is to recognize the need to completely define your system and processes. The second law will help you. I want you to recognize that when we have fossil fuels, biomass, that what we do is we can define a single operating point. Our comfort zone is here. When we bring in renewables, solar, wind, that are variable with respect to time, it requires a different approach. You need to do simulations. And the simulations are going to end up being MATLAB, Excel. How many of you do C++? Okay. Probably an overkill for some of this, but a very powerful tool. You need to be looking at what happens over the day. The gentleman that asked me the question after class about averaging cloudy days, okay, I gave you 1 day. If you were doing this for a product, you'd be looking at a minimum of a year's worth of data, and it would be average weather data. So you need the simulations. The simulations must be accurate. If you don't, you're going to underestimate capital costs, the rate of return, and the performance. How many of you are familiar with this ROI? A bell doesn't count. Okay? This is the rate of return. If you come up and tell me that you have a battery that is 3 times cheaper than lithium ion, that has an energy density that's 4 times larger than lithium ion, that has a lifetime as twice as much, and I'm the investor, I'm not an engineer now. My first thing is, well, what's your expected ROI? And if you look at me the way you're looking at me right now, and I'm hoping you're understanding my English and reacting to the question, I'm going to go, oh, this guy doesn't get it. Investors don't care about enthalpy, entropy, exergy. This is what they're looking at because they're willing to give you this. Performance is what makes it work. Okay, can I go on to the next slide? The design. The second law. It gives us our limit, the best that we can do. Okay, Professor Lienhard had a fantastic example of the article that clearly exceeded the limit. This is all important when you start a project. Okay, and the RO example I'm quoting actually was done to identify the losses, much as what I did with the solar example. And finally, there's many complicated pieces. Last slide. There's a lot missing. I didn't talk about energy storage. Energy storage is the next big thing. I have a research associate who is funded by a company with the sole purpose of coming up with energy storage products, mainly aimed at batteries, but energy storage is all important. Economics. I did not really do an economic analysis, and one needs it to really make this. Society. 240 soccer fields versus probably 2 soccer fields for the reverse osmosis plant. Probably 1. Are you willing to trade land for removing a fossil fuel source and CO2 producer? Earlier we talked about, are you willing to give up agricultural land to produce water? Okay, these are all things that we can help answer, but society has to weigh in. And regulations and government subsidies. Did Enrico in any of his talks mention that most of the profits of the distributed heating projects in Italy come from the government subsidy? Okay. Okay, I just said it. In Italy, they heavily subsidize a lot of alternative energy systems. Germany tried to do that, and they are running into the government did not get back the payback they expected on that. Yeah. Yes, yes. Finally, I want to get to this last item. There are other desalination processes and power sources, and Your mini project will go through some of that. But I want to get an end right here. We have many problems. Over the last day and a half, I have just learned of other problems, other situations, new solutions. And to put it very simply, and you've heard this, we need your creativity. You need to think outside the box. You've heard this from many of us in the panel discussion, Lienhardt Sr. Okay, you are the future, and I'm comfortable, but be creative. We're going to put you into very rigorous courses. We're going to put you into courses where, we're do it my way. Look at that as preparation. A preparation for when you're waiting for the bus. I take commuter rail subways. Platform time is wonderful thinking time. When that idea hits you, have the tools to make sure that it works, to optimize it, and to know how to get it implemented. Thank you. I'll take questions. I told them mini project due next Tuesday. Okay. Yes. No questions. See.
Could the land problem requirement be solved by installing the salination units in the clients' houses?
The question, you're on tape, so I don't have to. I hadn't thought of that. But that would be one interesting thought, that instead of circulating fresh water, or if you had a brackish well, that you would do this on an individual basis. I would have to look at the numbers, or you could look at the numbers. When I visit Mexico, I am always intrigued, impressed. You all have water tanks on the top of your house. And silly me, I thought they were all solar hot water heaters. But, you have a fairly flat roof area. I hadn't thought of that, okay? But it would probably be something that would be worth looking at, especially since the user would actually be controlling the consumption. It's an interesting idea. Just haven't thought of it. So thank you.
We were looking yesterday at the Excel sheet you sent us, and a question came out about the time interval.
Oh.
You said you could do it like 15 minutes apart. But we didn't find how that affected the final energy, the final formula for energy.
Okay, can you bring up the Excel sheet? The Excel sheet I gave you has hourly increments.
Yeah.
I'm assuming that the incident power is linear between each of those points, so that when you integrate that, in other words, multiply it by 1 hour, you get the energy that is incident for that hour. And if the linear assumption is incorrect. If you go to 15 minutes, you might see early in the day that the linear line is not a good approximation, that it's a little more curved. That's the only way it would affect it. Most people do hourly, but if your system that you're modeling is responding on a half hour time frame, then you really should be using half-hour increments. Okay, did that answer your question?
Yeah, kind of. I just wanted to know where the clock time affected in the other when you
Where the clock
resolve your
time,
energy. Yeah.
it affects the hour angle.
Oh,
And then, can you go down? Keep going, keep going, keep going, keep going. Okay. On line 40, row 40, would you highlight would you change the font color on 40 to black? Okay. This is total incident. If you multiply this by 1 hour and sum them, you'll get the total energy. Okay? If these are not linear between, you'll get a different answer with shorter. Feel free to add columns and cut and drag.
yeah, because we tried to change the time interval, but it didn't change the bottom, so that's why.
Okay. Can I ask you something? This one is still on Boston, right? The other class went to Salamanca. If you go up to the altitude, if you change this to Salamanca in July, this number was probably fairly high, which means you're not quite at sunrise. Okay, you need to work your way back to sunrise. Okay? Thank you for your question. Can I make one other comment? Okay, if you email me with a question, very often, if it's about the Excel sheet, send me your Excel sheet. Okay, because it's much easier. If it has to do with the calculations and you've written them out, scan them. Take a picture of it with your camera. Send it to me. I can download it, make my comments on it, answer your questions. It's much easier than trying to write pages of questions. Okay, thank you.
¿En Irapuato hay alguna pregunta? Okay.
Put
Thanks.
them to sleep.
Thanks, Professor Kowalski. This is a little diploma for you.
Thank you.
We appreciate your participation.
Thank you.
Let's continue with the poster session.
Can I just say one? It's a pleasure to come and teach you and interact with you. I know I put some of you on the spot. Some of you just really like it. Okay? But I always leave feeling much more enriched. Thank you. Gracias.